Hello everyone, this is Bandgar S.S. working as assistant professor at Department of Physics, Kettichan College, NASA. Today we have going to discuss S.Y.B.Sc paper 2nd semester 3 instrumentation. In this video we have going to take the chapter of signal conditioning and processing, and in this chapter we have to cover the topic of operational amplifier and their applications. So starting with introduction of op-amp, most of the electronic equipment requires to amplify weak signals. That's why we have to require signal conditioning and processing circuits. As the operational amplifier is widely used in signal conditioning and processing circuits. The operational amplifier have many advantages. That's why we have to use operational amplifier in various signal conditioning and processing circuits as an amplifier to amplify the weak signals and conditioning and processing the signal. That's why we have to use a operational amplifier. So the operational amplifier have many advantages, like as a very high gain, high input impedance, low output impedance, negative feedback, infinite bandwidth, infinite CMRR, zero offset, D negative feedback, infinite slew rate, infinite PSSR. PSSR means power supply rejection ratio. CMRR means common mode rejection ratio. Is depending on the gain. Now next concept is the symbol of op-amp. So op-amp has the two input terminal, two voltage input voltage sources and output voltage. Two supplies are required, positive and negative, and two inputs are inverting and non-inverting. The circuit symbol of op-amp as shown in figure. So V plus is the non-inverting input, V minus is inverting input, V output is the output voltage of op-amp, Vs plus is the positive power supply, Vs minus negative power supply. So that is the terminals of the op-amp. Now op-amp has the various applications. So starting with a first application, current to voltage converter. See the diagram, given to the input as a current, and here you will get the desired output voltage. So RF is the feedback resistor, RI is the input, R is the source resistance, Vp is the positive terminal voltage, Vn is the negative terminal voltage, I is the current, I1 and I2 across a R in and RF. The voltage gain equation of the inverting amplifier is V0 upon Vin, that is the gain, is equal to minus RF upon Rin, because of it is the inverting amplifier. Therefore, output voltage of inverting amplifier is equal to Vin upon R1 into RF. However, since V1 is equal to 0 and V1 is equal to V2, so V1 upon R1 is equal to R2 and V0 is equal to Rin into RF. That is, the output voltage is directly proportional to the input current. So that's why we have to say that is the current to voltage converter. Thus, output voltage is proportional to the input current and circuits work as a current to voltage converter. This circuit is also called as a current control voltage source or trans-impedance amplifier. Second application is the voltage to current converter. See the diagram, given to the input voltage across a RF feedback resistance, we have to get the current. So the complement of current to voltage converter, that is the voltage to current converter. The circuit diagram, I1 is equal to Vin minus En upon RR, that is the input resistance. And since Vn is the virtual, then Vp and Vn is equal to 0, then I1 is equal to Vin upon Rin. But we have to I1 is equal to I2, therefore I2 is equal to Vin upon Rin. That means the current is directly proportional to the input voltage Vin. it is a independent of load resistance R2, or so Vin is a directly proportional to the okay. Next one application is the buffer amplifier. So buffer amplifier, it also known as the unity gain amplifier, voltage follower, it also known as the voltage follower. So we know that the gain of non-inverting amplifier is AV is equal to 1 plus RF upon RE. So see the diagram. There is the second terminal is directly connected to the input to the output. We make a RF is 0, R1 is the infinity. We will have an amplifier with gain if exactly 1. It is known as unity gain amplifier. In this non-inverting amplifier circuit, RF is a plain wire which has effectively 0 resistors. R1 is an infinite resistor obtained by not having any connection to the ground at all. This arrangement is called as a op-amp as an voltage follower or buffer. The buffer has an output that exactly mirrors of the input. The importance of this circuit does not come from any change in voltage. Now next one is the sampled and hold circuit. So it shows the sample and hold circuit block diagram being given to the input sample and hold circuit, and you will get the sampled value and you will get the command terminal, and this is the block diagram of SH circuit. And second diagram is the N channel JFET as a series switch. So here JFET acts as a switch on and off conditions. It is usually represented as SS circuit. Use of analog to digital converter to sample the input analog signal and hold the sample signal. In SS circuit, analog input signal is sampled for a very short time interval, 1 microsecond to 10 microseconds. The sampled value is held until the arrival of next input signal, which is to be sampled. The holding time of sample is few milliseconds to second. The sampled hold circuit basically consists of two components. First one is analog switch and second is the holding capacitor. JFET or MOSFET can be used as analog switch. Example, JFET as a series switch. Can be shunt switch also. When VGS is 0, then JFET acts as a closed switch. When VGS is negative, then JFET acts as a open switch or blocked in. For holding the sample, capacitor can be used. Now next concept is the sample and hold amplifier. See the diagram. To buffer amplifier connected by a to JFET switch. A sample hold circuit consists of switch, hold capacitor and buffer. This circuit has two basic and distinct operations. First stage input signal Vin applied to the first op-amp is sampled. During sampling period, the JFET is turned on by applying VGS 0 volt. The transmitted signal charges the holding capacitor and voltage across the capacitor rises to the level of the input voltage. The output voltage is equal to charge on capacitor. In second stage, at the end of sampling period, JFET is turned off by applying sufficient negative voltage to VGS, and holding capacitor C is isolated from the input signal. The last value sampled is held until the arrival of the next input signal. To avoid a small dropout of the capacitor voltage during the hold period due to the various leakage currents, amplifier A1 and A2 gain is equal to 1 are used as a voltage follower circuits. The characteristics of a sampled and hold circuits are: first one is the acquisition time, that is the TAC. It is the time required for the holding capacitor to charge up to a level close to the input signal voltage during sampling. Acquisition time depends on maximum output current of op-amp, slew rate of op-amp and RC time cost. Second one is the aperture time, TAP. When hold command is given to SS circuit, then circuit stops any changes in the input signal and hold the latest sampled value. Sampled and hold circuit follow the changes in input voltage for a very short period of time even after receiving the command. This period is known as aperture time of SS circuit. Now next characteristics is the hold mode's settling time TS. Even after the hold command is applied, it takes a certain amount of time for output voltage to settle within a specified error band such as 1% or 0.1%. Next characteristics, voltage drop. The leakage current causes voltage across capacitor to drop down. This is known as voltage drop. The leakage current can be minimized by using perfect dielectric material such as polo carbonate, Teflon, polythene in capacitor. Now next, aperture uncertainty, that is the change in TAP. Aperture uncertainty is the variation in aperture time from sample to sample. Next characteristics of HS circuit is feed through. In the holding mode, switch is off state. Because of stray capacitance across the switch, there is small amount of AC coupling between output voltage and input voltage. The variation in output voltage with variation in input voltage, this is known as feed. Now next, hold step. At the time of switching from sample to hold or from hold to sample mode, there is unwanted transfer of small amount of charge between switch driver and capacitor. The changes is voltage across a capacitor and changes in output voltage are referred as a hold state. Now next concept is a filter. Filters is a device to remove the unwanted signals. So filter is desirable to amplify a signal in given range of frequency while suppressing the other frequency of signal. Using operational amplifier of filter, it is formed as an active filter. The active filter are a conjunction of passive elements like as a resistor, capacitor with active element such as operational amplifier. So using an operational amplifier, filter has some advantages. The advantages are, first one is the RC active circuits contain non-inductors, so it is easily to integrate. Second one, it can be used at very low frequencies where impractical use of inductor. So there are two types of active filters. First one is the low pass filter, second one is the high pass filter. So starting with a low pass filter, at very low frequency capacitive reactance Xc is equal to 1 upon omega c becomes very large and its circuits acts as the inverting amplifier with gain minus R2 upon R1. When frequency of the input voltage is increased, capacitive reactance of the capacitor decrease, thereby decreasing the voltage gain. At infinite frequency, the gain approaches zero because then capacitor appears short. Because of this, circuit passes the low frequency but blocks the high frequency. The point at which frequency becomes decreasing known as cutoff frequency. See the frequency response of low pass filter. It passes the low frequency and when it is become high, then it is the block or decreasing. So FC is the cutoff frequency. Now see the circuit diagram of active low pass filter. So here we have to use RC combination. So there is the input is a resistance and feedback is a capacitor, and that is the inverting amplifier. So input impedance Z1 is equal to, that is the R1, that is then output impedance is 1 upon Z2 is equal to 1 upon R2, 1 plus 1 upon j omega c is equal to 1 upon R2 plus j omega c. The ratio of impedance is Z2 upon Z1 is equal to R2 upon R1 into 1 upon 1 plus j omega c. The absolute value of ratio impedance is mod of Z2 upon Z1 is equal to R2 upon R1 into 1 upon square root of alpha plus omega square c square R2 square. This ratio shows that the gain is maximum at low frequency and decreases with increasing in frequency. Next type of filter is high pass filter. So see the diagram, frequency response of high pass filter. It blocks the low frequency and passes the high pass frequency. When it starts increasing at certain point, that is called as a cutoff frequency. At low frequency, omega is equal to 0, the capacitors appears open the gain and hence output of the amplifier is very small. But the high frequency, the capacitive reactance of the capacitor is very low and it acts like short circuited and the circuit becomes an inverting. Because of this, circuit passes the high frequency but blocks the low frequency. The point at which frequency becomes increasing known as the cutoff frequency. Now see the circuit diagram of active high pass filter. There is the input of capacitors and feedback is the resistors, and given to the inverting terminal and non-inverting terminal is ground. So it is the inverting amplifier. The input impedance of the circuit is given by Z1 is equal to R1 plus 1 upon j omega c. So is equal to j omega c R1 plus 1 upon j omega c. The output impedance is Z2 is equal to R2. The amplifier gain is equal to minus R2 upon R1. The gain of amplifier is Z2 upon Z1 is equal to j omega c R2 upon j omega c R1 plus 1. The absolute value of this ratio is equal to mod of Z2 upon Z1 is equal to omega c R2 upon square root of 1 plus omega square c square R1 square. Now next concept is the instrumentation amplifier. See the diagram, 3 op amps are used. Most of the non-inverting amplifier, 2 are non-inverting amplifier and second one is the differential amplifier or a difference amplifier, or it is controlled by gain R1. The instrumentation amplifier has some advantages. First one is the very high CMRR, common mode rejection ratio, high input impedance, very high gain, very low DC offset, low drift, low noise. So these are the various advantages of instrumentation amplifiers, so that's why it is used in various applications. Instrumentation amplifier is combination of 3 op amps that are grouped into 2 stages. First stage are 2 op amps, each are in non-inverting amplifier. Second stage is differential amplifier that may or may not have unity gain. The instrumentation amplifier, initial amplifiers like non-inverting ones are considered as a buffer. It can be evident from the circuit. For those 2 buffers, 3 resistors are connected. These value of the resistor connected in the circuits will equal except that resistors are 1. That is the potentiometer or variable resistor. At A1 in the circuit, voltage will be considered as a V0, and at A2 the output voltage considered is equal to V02. So you will get the V01 minus V02 upon V1 minus V2 is equal to 1 plus 2R2 upon R1. That is the inverting equation. The potential drop generated at the R1 is the difference between the voltages V1 and V2. Because of this region, current flow through that point, that is through R1. This indicates that there is no current flow is observed through the feedback. Then this results in the same amount of the current flow through resistors R that are connected above and below in above circuit. The voltage drop between V01 and V02 is connected to the inputs of the differential amplifier E3, amplifies it by gain 1, assuming all resistors are values same. Vout is equal to V1 minus V2 into 1 plus 2R2 upon R. Thank you.